Okay, so welcome to lecture 3. And welcome to the online residential. So we're talking about just an introduction of quantitative methods. In lecture 1, we described and defined the various and different variables, types of variables and types of data. Okay, so yesterday, we're talking about how to describe data. You have to take in consideration what kind of data you're dealing with, and then you can make a decision of how to describe it, either graphically or tabulating the information or the data that you have. Okay, so today we're going to look at describing data numerically. We also call this a measure of central tendency, location, variation, and spread. Okay, so yeah, that's our topic. So this time we want to see how we can compute the mean, the median, the mode for a set of data. Okay, how to find the range, the variance, the standard deviation, and construct the box and whisker plots. We're also interested in how to find the coefficient of variation. Okay, so we will not do the z-scores. We're going to do this in probability distributions. So we will not do this part for now. Okay, so yeah, the mean, the mode, and the median. We are somehow familiar with this. Okay, now we're told that the mean, the median, and the mode are actually a measure of central tendency. We want to see how the data is centralized. Okay, so what is the other word for the median? The mean. The mean. There's a common word or common name for the mean.
Average.
It's the average, yeah, or arithmetic average, or just average, yeah. And the median, when we talk about the median, what comes in your mind? Or what is the median?
It's actually an observation now. Our score at the mid, often at the mid of a selected.
The mid of a selected.
Yeah, mid of a selected scores.
Okay. Oh, okay. And what about the mode? What comes in our mind?
It's the common score observation.
Pardon?
It's the common score or observation.
The common, the most common?
Yes.
Yeah. Okay. So we have the geometric mean and the mid-range. We're going to see this. Then we also talk about, when we talk about the measure of location, we talk about the weighted mean, percentiles, and quartiles. Now, when we talk about the weighted mean, we just want to see how different weights affect the mean. Like, we're not taking everything as equal. We want to see how other variables affect the mean. So we're also going to see this. Then the measure of variations include the range, interquartile range, variance, and standard deviation, and coefficient of variation. Okay, so we now go into just a summary. I think that's what we have talked about. Okay, so the mean is just the sum of all observations divided by the number of observations. And we start with ungrouped data. Okay, so the formulas that I'm going to give you here are for ungrouped data. So we saw yesterday that we could actually group some data into a frequency distribution, right? Now, if we haven't grouped the data, we just call it ungrouped. So these are the formulas for ungrouped data. So for ungrouped data, to find the mean, we just sum all observations and divide by the number of observations. Now, note that we have, this is read as X bar, okay? X there just means the sample mean, okay? X bar is a sample mean, and that Greek letter there is mu. Mu, it means the population mean. So whenever we're talking about the population mean, we'll be using the symbol mu. And when we talk about the sample mean, we'll be using X bar. That. Yes. And so the median here there just shows you the number, the observation that is on the middle of the data set. Okay. Oh, okay. So, and the mode we see is the observation of the highest.
Sorry, can you just repeat what the Greek letter or symbol there means? Yeah, that one.
Okay, so the Greek letter is spelled mu. Okay, but is read as mu. Mu.
Okay.
Yes. So that mu is the symbol for the population mean. Population mean. Yes. So the population mean is denoted by mu. But how you get that mean is the same as how you get the sample mean, except not just the n there, the one you divide by is the number of observations of the number of observations in the sample for the x, and the capital N will be the number of all observation in the population. Okay, yeah. So, but how we compute the mean is the same both for x bar and mu. X bar is the sample mean and mu is the population mean. Okay. So the median is just the observation in the middle there, and the mode is the observation with the highest frequency. Okay, now the weighted mean is still, we have X bar for the weighted mean. So here we're using the sample to find the weighted mean, and there we're using the population to compute the weighted mean. Yes. Now, you see in our example how we compute the weighted mean. For the mean here, we take all observations to be equal. Okay, like, yeah. But for the weighted mean, we consider weight of every observation. And that is why we call it the weighted mean. We want to see how each observation affects the mean. And that mean that we compute is known as the weighted mean. So you see from an example. Okay, so so the mean, I think we have, we understand this, don't we? Just the summation of all observations. Yes. So that sum, okay, this is read as summation of xi from I is equals to 1 to n. Okay. So that is summation of xi from I to 1. So there we're just saying we're summing xi's starting from when xi is 1. So we'll sum x1 plus x2 plus up to xn. So that is just basic math that you should know as a statistician. Yeah. So you're just summing xi's. Okay. So even that's also the same for the population mean. Okay. Okay, I've clicked on the next slide, but it seems
it's moving,
okay. Okay, so just waiting for the next slide. Don't know why it's taking long to. I hope it doesn't. Okay. So the most common measure, the most common measure of central tendency is the mean. Okay. So the mean, like in that case, is 3. So this is like just having 1, 2, 3, 4 up to 5. Then you add everything, divide by 5, you find the mean is 3. When you have 1, 2, 3, 4, and a 10, add everything, divide by 5, should have a 10. So that is your mean. Now, the median, we say it is the measure in the middle of the data set, or the measure that divides the data sets into halves. So for the median, the first thing that you do is to arrange your data set in ascending order. Okay. Then you can find the number on the middle. Now, if your n is an even number, then the number on the middle is gotten from the 2 that are on the middle, and you add and divide by 2. I think you'll see from an example. Like there, we had 5, so the number on the middle is 3, and that there were also 5, so that was clear. Let's see from the next. Okay, so you can see if n or the capital N is even, then the median is the average of the 2 middle numbers. Okay, there's some noise in the background. Okay, so the mode is the value that occurs often. Okay, I think we can read that and we are able to follow. Okay, so this is an example on weighted mean. So as you can see here, sample of 26 repair projects. So here we had a number of days to complete 5, and the frequency of the projects completed is 4. Number of days taken was 6. The frequency of the project completed in 6, repair projects completed in 6 days is 12. So as you can see, different projects took different days to be completed. So in this case, we're interested in the weighted mean. So we want to find the weighted mean, we just multiply each day by the frequency. Okay, some noise in the background again. Okay, so we just...
I think those with the mics on, that's where the noise is coming from.
Belinda, please turn off your mics.
Okay, but the sound, Kanyika, is it my mic here can get me clearly, or what's the problem here? You're saying sound is so poor?
It's only Kelma's mic that's disturbing all of us. If you can switch it off, we'll appreciate it so that we can hear you.
Okay, Kelma.
Kelma, are you aware your video is on? And your mic? Oh.
I can see Kelma Luaya's mic is off, I think, for now. Okay, maybe we can proceed. Okay, Kanyeka says the sound keeps breaking. Is it the same also even for others?
No. For me, it's loud and clear.
Okay.
For me, it's loud and clear.
I can also get you very clearly.
Yes.
Okay. Okay, that's good that it's clear. Okay, so let's proceed. So that is how we get the weighted mean. So we're interested in seeing how the number of days completed affects the mean. So that is how we compute the weighted mean. Okay, so for the weighted mean, just know, but I will not ask you to compute the weighted mean. So just know that sometimes it is good to see how other variables affect the mean by computing the weighted mean. Okay, so that's a review example. Okay. Okay, I'm clicking on the next slide. Okay, so those we can find, I think, an average of those prices. Okay, I'm trying to click on the next slide and it's taking. No? Okay, maybe we should just wait a bit. Okay, so in one of the examples, or I mean the exercises, I need you to find the mean of 5, 3, 8, 5, and 6. Okay. So before we go to that example, since our next slide is here, so we can find the mean for that example. Okay, the mean, we're just adding up everything and dividing by 5.
By 5,
yes. And the number, the number on the middle is just that.
300.
Okay. And the most frequent, which is the mode, is 100,000. Yes. Okay. Okay, so the mean is generally used unless extreme values exist. Okay. And the median is often used again as well, since it's not sensitive to extreme values. Okay. Okay, what does that mean? Maybe before we leave that, I'm assuming that people understand it. Here we're saying that the mean is generally used unless extreme values exist. Anyone? What does it mean? Okay, so you can take the mean. If you have, say for example, you want to find the mean of 1, 2, 4, and 20. Okay, so what is your mean going to be? 1, 2, 4, and 20. What's our mean there? 1, 2, 4, and 20.
6.75. 6.75.
Okay. Chanda, are you computing this?
6.75.
Okay. So 6.75. So we have a 20, which is slightly bigger than all the values. Okay. So what if we had 1, 2, 4, and 100? What's our mean going to be?
And 6.75.
So our mean is going to be 26.75. Okay, but what do you notice? We have an outlier there. Okay, we have something that is way bigger than all the other values. We have 100. So our mean is 26. But when you look at these values, they're actually very small. They should have an average over, the rest of the values. The average should be around these values. Okay, but because of this bigger number, which is 100, we have an average of 26. So we are saying that we generally use the mean unless we have extreme values, because having extreme values may give us a wrong perception of the data, or wrong conclusion of the data that we have. Okay, so as long as the data set is within a considerable.
Huh?
Okay, there's some noise.
Mama mati atirira bwera.
Oh,
There's some
Brighton
So I get one.
Brighton, turn off your mic.
Which is written or not written?
Which is written?
Okay. All right.
Yamushe niti.
Ma?
Yamushe yoneka bwanji bati.
Nito mina phone nzaleta manje manje. Geto mina tenga.
Muzaona yeye aoneka mushe whether written or si written ndio mukatenda.
All right.
Right.
Okay.
Brighton. Hey.
About the light, switch off your mic.
You're disturbing Brighton.
I apologize. I thought I had switched off my mic.
Yeah. Okay. So yeah. So the example that I gave, the values that I gave, I just wanted to explain more on the slides. So Mkuka, there isn't another slide, but I just brought that up to explain more on slide number 13. Okay, so again, the median is often used since it does not take into consideration extreme values. So in this example, where we had 1, 2, 4, and 100. Okay, so we can easily choose the number of the number in the middle without the extreme value doesn't affect anything. Okay. So we proceed. We'll look at a measure of spread. Now, the mean, median, and mode, they show you how the data is centralized. Okay, but now sometimes we're interested to find out the spread of the data. Okay, so yeah, so sometimes the data can be left skewed, right skewed, or symmetric. Now, when it's left skewed, it means that the tail is on the longer tail is on the left. Okay. So when it's right skewed, okay. Mr. Kel Malwaya, please kindly put on a shirt.
For real, Monty that distract.
You should just turn off his camera.
Okay. So the left skew just implies that the longer tail is on the left. Now, what this means is that most of your data is centralized, is on the right, okay? But you have few values that are small, or that are few values, what's the word again? Okay, so you have few values that have little magnitude. For example, if you have a 1 and a 2, but the rest of the data are maybe say 20, 30, 33, 40, and up to say maybe 50. So you find that when you graph this data, most of it will be there, but you have few values that are smaller. So they are pulling the data on the left. That is why it is left skewed. Okay. Now, here we are concerned with how the data is spread, remember. Now for symmetric, the data is just evenly spread. The data on the right is actually equal to the data on the left. Now for the right skewed data, you have most of the values on the left, okay, but few values which are higher. So these higher values are pulling the data to the right. That is why the tail seems to be, the tail will be longer on the right. So that is right skewed. Symmetric. Symmetric, we also refer to this as uniform. Okay. And yeah, and left skewed. Okay. So that is with the spread of data. So it's either symmetric or skewed. We also have a measure of location. We want to know how the data is located. Is it on the middle? So the median is also a measure of location. Is it on the middle? Is it on the at least 25th position, like 25th percentile? Okay, or 75th percentile. So our data can be grouped, or we can find some percentiles to demarcate where each observation falls, whether it falls in a percentile less than 25, or between 25 and 50, or after 75%. Now, we did most of this, I think, in grade 12. You remember those ogive tables? We look at them, and okay, there's some noise. Some noise. The babies in the background. Simulea Zemba. Okay, the mic is off now. Okay, so yeah, so that is, I was saying that we did so much of this in grade 12 statistics. We had some ogive table, graphs, and from that you would demarcate your data set, okay, to find the 25th, 50th percentile, or 75th percentile. Now, okay, so the percentages of the data is just between 0 and 100, and I think this is something that we know. Okay, so the pth percentile, so the pth, we're just saying p can be any percentage. So pth percentile in an ordered array, okay, is any value in the ith position, where I is just p over 100 multiplied by n plus 1. So we are interested to find that position where a particular percentile falls. So the 60th percentile in an ordered array of 19 values is in the 12th position. So like 60 percentile, so I just say 60 over 100 multiplied by 19 plus 1. Okay, so that is the 12th position. So this formula just helps us to find the position where a particular percentile falls. Okay, so so these are the percentiles we can have there. So after the 25th percentile is also known as the first quartile. The 50th percentile, so 25 plus 25, 50. 50th percentile is also known as the second quartile, but this is also known as the median. Remember, it's in the value, the position that divides the data set into halves. So it's also known as the 50th percentile and also known as the median. Now, there, when you have 75, 75, 75th percentile is also known as the third quartile or the upper quartile. So Q1 is known as the first quartile or lower quartile. Q2 is the median. Q3 is the third quartile or the upper quartile. So from that example, you can find the position. So that is for ungrouped data. Remember, I said everything that we're doing now is for ungrouped data. Now we can make a summary of our data set or of our the measure of location. Okay, so using 5-number summary. The 5-number summary is just the minimum value of the data set. Q1, which is the lower quartile. Q2, which is the median. Q3, the upper quartile, and the maximum value of the data set. So you can now construct your box plot. This is what it looks like, box and whisker plot. So you put your minimum value there, then you put your first quartile, your median, the third quartile, and the maximum value. Now, you scale this up, okay? You scale this up. Of course, it doesn't need to be exact, but if you're going to put your maximum value, your minimum value as 10, okay, and your first quartile is 13, then this distance should show that, okay, it's a little bit smaller. Okay, now if your median is, say, 17, so from 13 to 17, this distance also is supposed to show that it is longer than the one at first, because the numbers here are not so close. The difference in the numbers here is smaller than that difference. Okay, so maybe you see from an example. Okay. Okay. So the box and central line are centered between. Okay, so I think here I didn't put an example, but okay, let's do this. Let's go to the next slide. I think it will be able to. Okay, yeah. Now you see, say your minimum value there is 10, okay, and your Q1, okay, Q1. So the minimum value there is 10, and Q1 is 14. Q2 is 20. Q3 is 21, and the maximum value is 22. Okay. So I say the minimum value there is 10. Q1 is 14. Q2 is 20, Q3 is 21, and the maximum value is 22. So the distance between the minimum and Q1 is 4. Okay, so we can assume that this is that 4. Okay, and the distance from Q1 to Q2 is 6. So you can see that this distance is a little bit longer than that, is almost longer than this distance. Okay, but this just shows you that the distance between Q2 and Q1 is actually smaller than the distance between Q1 and Q2. Okay, so the distance between Q2 and Q3 is smaller than the distance between Q2 and Q1. So you have to observe, you have to draw to some scale, because you have to show how you have to show the locations. Okay, so there's some scaling there. And even here, you can see that the difference between Q1 and Q2 is actually smaller than the difference between Q2 and Q3. And the rest of the data, and the difference between Q1 and the maximum value is also longer or bigger than the difference between Q1 and the minimum value. So actually, we can see the location and the spread from the box and whisker plot. Here, this shows a left skewed data, a longer tail on the left, and that is equally distributed, so it's symmetric. And we can see a longer tail on the right, so that shows that it is right skewed. So I can ask you to construct a box and whisker plot, and from there you can conclude the spread of the data set. Okay. Then you can also see the spread of the data set through a bar chart. The bars, you can use the bars to see how the bars, the shape that the bars follow. So you can see, you can conclude whether it is right or left skewed, or it is symmetric. Okay, so we should be heading to, okay, there is an example. I think you can follow it. Yes. There is an example. Okay, measure of variation. Now, sometimes we are interested to find the variability in the data. Okay, and we usually use the variance and standard deviation and coefficient of variation to find the variability in the data set. Okay, so the range just computed by the maximum value subtracted from the minimum. I mean the minimum subtracted from the maximum value. We taught this yesterday. We were talking about construction of yeah. Okay, so please be patient. We are halfway. We still have another half. We are halfway. So example on box and whisker plot. That there is a slide there. I think I just skipped it because I explained on that. I explained on that. So just try and follow it on your own. If you have challenges, you can get back to me. I'm sure you can follow it from here. Okay, so the interquartile range is just the third quartile minus the first quartile. So once you have computed Q3 and Q2, you can then just find that difference, and it will be your interquartile range. Okay, so that is just shows the interquartile range, Q3 and Q3 minus Q1 there. Okay, so Okay, so to find the variation in our data set, we compute the sample variance. So sample variance is denoted by S squared. Deviation variance is denoted by, that is sigma squared. That is the Greek symbol there. Sigma squared. You will be meeting this, so you need to know. Oh, so you're saying that you didn't get the previous slide. No, we have not done an example on this, on the box and whisker plot, but I've just explained how to construct it. Okay, so are there other people with a question on the box and whisker plot?
Okay.
Madam,
Yes.
I don't know. It's just a suggestion. Is it possible you could have a whiteboard so that you could be writing for us? Maybe we can be seeing through your video, because going through the slides is like reading and it's not making much sense.
Okay, so we are still working on having the board. Yeah, but the problem with having a board like on the background here, if I had my board on the background, the things that I would write would not be so clear. Yeah. So the slides are actually better because you can see. Yeah. Except the computations. Except I'm not doing the computations. But there's another one that I'm going to upload, a scanned document where I have done some computations and then you can follow. But we're working on that. But the problem is that we don't have, what can I say? Okay, we're working on it. I'm sure the next lectures will get better. So I'm thinking of just us going through this example on the since I've got a question from okay, so we have that data set. We have 0, 2, 2, 2, 3, 4, 4, 3, 4, 5, 5, 10, and 27. Okay, so this is our data set. Our minimum value is 0. Okay, and our maximum value is 27. Okay, so this data is already arranged for us. Now, how did they find that Q2? So we're looking for the 25th percentile. We're looking for 25th percentile. How did they find that Q? So the position of the 25th percentile, we said we have the P percentile, the formula?
100.
So we said I is equals to P over 100 multiplied by N plus 1, right? What is our N there? How many numbers do we have? 1, 2, 3, 4, 5, 6,
11.
7, 8, 9, 10, 11. 11, right?
Yes.
Okay, so we're looking for the position of the 25th percentile, which is Q1, right? So for the 25th percentile, we're saying I is equal to 25 over 100 multiplied by 11 plus 1, right?
Plus 1, yes.
So what do we get? 25 times 12
is 2.
We get 3, right? Yes. So what does that 3 mean?
It's the third number from the beginning.
Okay, so 3 is the position, right? Of the 25th percentile. So, and since this data is already arranged, we just count 1, 2, 3. So the value on the third position is the 25th percentile. So we then write Q1 is equal to 2, right? So remember, we already have the mean, which is 0, the max, which is 27. Yeah. And how do we get Q2? How do we get Q2?
It's the median, 50th percentile.
Yes, it is the median, but how do we get from this data set that we've been given?
It's 50 over 100. 11 plus 1.
Okay.
11 plus
7.
1.
Yes, there was someone
Which is 6.
saying something. Okay.
So it's 6th
Okay,
position.
so 6. So the 6th position, which is that. Okay.
Yes.
So our Q2 is 3. So how do we get Q3?
3 quarters.
I will be what?
75
I
over
would
100.
be 75 over 100. And
Okay.
11 minus, is it 11 minus 1?
Plus.
Plus
11 plus 1.
plus 1,
Yes.
yes.
9, right? So the 9th position, that is how we find our Q3, which is 5. Okay. So then we now sketch our box plot. Our minimum value is 0, right?
0.
Q1 is 2. So you can see Q2 is 3 and Q3 is 5. So the difference between Q1 and Q2, you can see that the difference between Q1 and Q2 is smaller than the difference between Q2 and Q1, right?
Yes.
Yes. So, and the maximum value is 27. You can also see that distance just shows you that the distance between Q3 and the maximum value is actually very long. Even if you left it here at 27, you're still okay. Okay. This having it ended your graph here. Okay. It still shows that this distance is longer than the distance between the mean and Q1. Okay. So what can we conclude about this? Is it skewed to the right or left?
It is skewed to the right.
Because we see there's a longer tail where on our right.
On our right.
Okay. Okay, so that is on the box and whisk cut. On measure of variations, I think we still have not done much on that. Okay, so that's what I started with before I got a question from Geoffrey. So the range, we can find the range, just the maximum minus minimum. Interquartile range is just the third quartile minus first quartile. Okay. So the variance is a measure of variability in the data. So the formula there just states summation over xi minus x bar squared divided by n minus 2, n minus 1, I mean.
N minus 1.
Okay. Yeah, so I say that is S squared for the sample variance and sigma squared for the population variance. And for the population, we are dividing by n. Okay. Okay, let me just get to the next slide. Oh, okay. So that is just This is the standard deviation. So this should always be at the back of your mind. The standard deviation is just the square root of the variance.
Yes.
Okay, standard deviation is just the square root of the variance. So when you have the variance and you're asked to find the standard deviation, that should just be a giveaway question, because you already have the variance and you just square root your answer to find your standard deviation. Okay, so let's have that example. We have 10, 12, 14, 15, 17, 18, 18, and 20. Okay, so the data has been arranged for us. The mean is given as 16. So what's the mode for this data set? The mode?
18.
18, right? Okay,
Yes.
and the median? What's the median?
15 plus 17.
15 plus 17 divided
Plus
by 2.
17 multiplied by 2. Plus 17.
43. 43.
No. 43 can't be an answer. Even if I've not computed, you have 10, 12, 14.
16,
The
it's
number on the
16.
middle can't be.
16.
Okay, 16. So the value that you find should be around these values that exist,
16.
because you're just simply describing the data set better. Okay, so you're just saying what is the value in the middle, what is the average. Even if I've not computed these values and you give me an average of, say, 35, okay, I might refuse, or maybe 57, okay. So it doesn't make sense. So you have to understand what you're doing before you even just underline your answer. Okay, so the standard, the sample variance there, the formula says, okay, so you can see the root there. Whenever you have the root, what are you computing?
A standard deviation.
What are you computing?
Standard deviation.
And you can see here, standard deviation just has S. So this is a sample standard deviation. Okay. So the sample variance is S squared. Okay. So there we are calculating the standard deviation. So the standard deviation is the square root of, we get each observation and subtract the mean. After subtracting that, we square it. Then we add to the next observation, subtract the mean, and we square. Okay. 14 minus, so in this case, our x bar is what? 17. Okay, so we can actually verify this, and we'll find that our standard deviation is 4.26. Okay.
X by 16.
Okay, I don't know what's happening with our. Okay, I think we're back. So we can try and compute that, but because of time here, I'm going to leave it for you to compute that. So here's just an explanation, I think, on the standard deviation, what it means. You have those values there. So you're seeing the values are somewhat spaced. So the standard deviation there is 3.3. And with these that are closer to each other, the standard deviation is actually 0.9. Okay, so when the data is closely located, then you have a reduced or standard deviation. But those that are evenly spaced, like you can see this, the standard deviation is actually 4. Okay, so that's what the standard deviation describes. Okay, so it seems. Okay, I'm clicking the next slides, but we're winding up now in the next 5 minutes, so we can't go beyond. Okay, so my next slide seems a bit blurred. Okay, so we should be winding up in the next 5 minutes. Okay. So it seems hope you have downloaded the slides, right?
Yeah.
Okay. Okay, so sorry for that.
Can be found.
So we'll not look at the empirical formula, but you can just study on that. Okay, Mr. Brighton.
Yes, please.
Brighton, please switch off. Can you mute your mic? Okay. So I said we'll be winding up. Okay, so then the other measure of variation is variation, which is just given by S, which is the standard sample standard deviation divided by X bar multiplied by 100. So you can easily do that. It's given as a percentage. So in assignment 1, particularly question 2, I think I asked you on this. So what you can do is just go back and just revise assignment 1, and you find that by this time you should be able to answer it all. Okay, so the next part of our section deals with grouped data, but it seems I underestimated the time that would take for ungrouped data. So we'll pick it up from here tomorrow. Tomorrow we're just going to concentrate on grouped data. Okay, so we'll not do the Chebyshev and the empirical formula. Okay, and we'll do the Z-scores in future lectures. Okay, so we'll end here. But tomorrow we'll start from grouped data, finding the mid, mode, and everything that we have done today, but we'll compute it for grouped data. Okay, so we'll end here. Any questions?
Yes, it does. I just have a question. Tomorrow we're meeting at the same time? Same time today?
Yes, 16. Or is there a problem with the time?
No. I just wanted to make sure. I didn't see the messages earlier.
Okay. Oh, okay. Yeah, 16 is okay. I think it's 10 minutes.
Okay, no, it's fine.
Okay.
Thank you.
So tomorrow we'll do much on grouped data. So that will be for tomorrow. Then on Friday, tomorrow is Thursday, right? Then Friday we'll start probability.
Yeah, okay.
So yeah. Okay, so thank you so much, and enjoy the rest of the day.
Thank you.
Thank you very much, and thank you for your time.
Okay, you're welcome. Okay, just want to see what is being typed before we go. Okay, so these guys are typing and typing quite a lot of stuff because I'm not seeing. So Mambo, you couldn't get what we're saying? Okay, thank you.